Hello, welcome to this session. Today's subject is fluid power engineering with the subject code of 18ME 55. We have been discussing quite often on module 2, so it's a continuation session. So we have seen just briefing out whatever we have seen so far, because we are at the fag end of understanding of hydraulic actuators, basically pumps. So hydraulic pumps we have seen where the mechanical energy is converted into the fluid energy. Whatever the energy comes from the motor, it is being converted into fluid energy by the pump. So it will pressurize the element there, and final outcome again the fluid energy is again converted into mechanical energy. So this interconversion is usually taking place from motor to pump and pump to the delivery, axial discharge. So where basically mechanical energy of the motor or the prime mover, any prime mover, is converted into fluid energy. That is a function of pump. So pump creates flow. That is what we have seen. And pressure is just an effect of resistance between the moving elements, maybe pumping elements like gears or vanes or maybe piston. So their movement with respect to each other, relative movement, will cause the resistance and the variation in the air pressure. So that is a result of suction and discharge. So that is just an effect of relative motion of the elements. So basic function of a pump is to create a flow. So that is we are familiar now. So varieties of pumps we have seen for various applications. So because I want different discharge at a different pressure, so I prefer gear pumps. Usually rotary type of pumps for few applications. We have seen all of them. Just I am revising and briefing out gear pumps and vane pumps. So usually they come under rotational rotary pumps. And we have seen a reciprocating pump, for example, piston pumps. So today's session is a fag end of understanding of all these. After understanding of all these three types of pumps, gear pumps, vane pumps and piston pumps, so now we are aware of their operating principle, working, construction. So we should be in a position to select a pump based on its application. So on what parameters I will usually select a pump? So that is the content of today's discussion or today's lecture. So content is pump performance, and one example with the help of numerical about the parameters which are called as performance parameter of a pump. So on which I come to a conclusion of maybe discharge or maybe volumetric displacement or its efficiencies. So these are few parameters which I will usually as an engineer should be aware of and should be able to give solution to the customer part or the application based examples I should be able to understand. So pump performance, I have been emphasizing on and keeping on reminding you that understand the term word by word. We know what is pump. Performance is what is expected from a pump. So to perform, that means to say to do some work. Pump activity we are already aware of. So to generate a fluid energy constantly at a particular pressure. So to perform that, so what are all the prime elements? Prime parameters of the pump which are deciding it. That we need to understand here. So just go one by one. So usually the material selected for the pump with the tolerance or clearance plays a vital role in understanding the performance of the pump. So what material you choose to create maybe gears or vanes or maybe the casing. So the prime elements contributing for creating the pressure and creating the flow, which are actively involved with the circulation process of the fluid or discharge. So they play a vital role there. What is the difference? What is the tolerance or clearance between the elements? What is the eccentricity? What is the width or what is the diameter of the gear or vanes? And what is the eccentricity between the vane, rotor and the camering, if it is a vane pump. So all those things will play a vital role. Okay, those are the parameters, maybe diameter, maybe physical dimension like diameters, width, okay, area. So all those, they come under physical dimensions. Okay, so like that, tolerance and clearance, what I am giving to the material in manufacturing precision. So one is material, and second thing is manufacturing precision plays a vital role here in the form of tolerance or clearance or space provided for the fluid flow. So these are the two things which play a vital role. So one is manufacturing process of pump, second thing is the precision, okay, of the material. Okay, one is material and one more is manufacturing process. So material, nothing but diameter, dimensions, diameter or width or eccentricity, okay, or area of the material. Manufacturing process is how do you achieve this, okay, dimension of the pump, okay. Manufacturing, how do you manufacture the gear with a tolerance, with a pitch circle diameter, or if it is a vane, diameter of the vane, width of the vane, eccentricity between the rotor and the cam ring. So all these plays a vital role. If it is a piston, how many number of pistons, okay, diameter of the piston, area of the piston, what is the RPM of the shaft, all these parameters play a vital role in, okay, giving the final output as a performance of the pump, okay, performance of the pump, the way how we analyze a student. So he is fed with so many number of subjects, he is being, okay, continuously evaluated in the form of internals, and finally with the help of examination we will usually give him the credits or what is his performance in this semester. So we will measure him with few parameters, okay, like a subjective, qualitative and quantitative aspect. Similarly, pump is also checked for its performance by using physical aspects like material aspects and manufacturing aspects. So what are those? We will see. So first thing is pump efficiencies. Obviously there are three efficiencies because pump usually the final objective of a pump is creating a, okay, mechanical energy on the shaft, okay, from the pump, okay, the fluid energy is spent on creating the mechanical energy, maybe rotary or reciprocating. So obviously torque plays a vital role in both the case, it may be rotation or it may be reciprocation. Torque or the force plays a vital role. There comes the mechanical efficiency aspect. Okay. Second thing is, okay, we obviously speak on fluid discharge. Okay, what is the amount of fluid is which is being pressurized, both in case of rotary as well as reciprocating pumps. So discharge of the fluid, whenever I say discharge, that means to say amount of fluid being, okay, from delivered by the pump. So what is the amount of fluid delivered by the pump? There comes volume of the fluid. So that means to say what is the volumetric efficiency of the pump. So second important efficiency. First one is torque, okay, because of the rotational aspects of the shaft. So with the, okay, number of rotation of the shaft being developed because of the fluid energy, that gives the mechanical efficiency aspect. Amount of fluid which is discharged by the pump, so that is directly contributing to volumetric efficiency aspect. So last one is combination of these two. So what is the mechanical efficiency? Because that decides discharge capacity of the machine. So torque of the shaft will decide, okay, the discharge of the pump, oil being delivered on the delivery side. So that is decided by the torque of the pump. So these two collectively will give us the overall efficiency of the pump. Okay. So how do we calculate it? So go one by one. Mechanical efficiency, usually efficiency is usually called by eta. The symbol we have shown here. So it resembles N, Greek letter N with a, okay, the tail end being prolonged. The tail end is prolonged quite a distance. Eta mechanical, mech, that is what we call the notation used for mechanical efficiency. It is a ratio of, okay, theoretical torque. TTH is nothing but theoretical torque to actual torque, T actual. So T actual is actual torque developed by the okay, by the pump, okay, in the shaft. So what is actual shaft being suffered or delivered by the pump, that is T actual into 100. We measure efficiency in terms of percentage. So to T theoretical, okay, torque, T is nothing but the torque here. So keep in mind, so where, okay, T is equal to torque, okay. So TH means, always remember, it is theoretical, and okay, ACT is a short form used for actual. So this holds good for, okay, upcoming explanations also. Okay, theoretical torque by actual torque into 100% gives me mechanical efficiency. Okay, similarly, volumetric efficiency, which is related to oil being delivered by the pump. So that is a ratio of actual, okay, discharge of the pump to theoretical discharge of the pump into 100. So this is vice versa of the mechanical efficiency. Okay, vice versa. That means to say, here it is theoretical by actual torque, here it is actual discharge by theoretical, okay, reciprocal of each other. Because Q actual is developed by the pump on the output side, always efficiency is output by input. So this is from the pump, this is being calculated for actual dimension being designed. Okay, here it is theoretical torque being calculated, actual is what is being suffered by the pump, the drive shaft of the pump. Okay, keep in your mind that these explanations are required so that you don't memorize the formula. Always things should be understood. That will help you in gaining more knowledge, so that you don't remember, you actually understand with the proper perception. Okay, so obviously overall efficiency is a multiplication of these two divided by 100. Mechanical efficiency into volumetric efficiency divided by 100. So these two collectively contribute for overall performance of the pump. Pump can be analyzed in two aspects, keep in mind. So one is the torque aspect, torque being developed by the pump. T theoretical by T actual will give us the mechanical efficiency. Second thing is, what is the work done by, okay, the pump, that is measured by using discharge. So amount of fluid being coming out of the discharge. So Q actual by Q theoretical into 100, that gives me overall, okay, that gives me volumetric efficiency of the pump. Okay, so combination of those two, eta mech into eta overall, will give us the overall efficiency divided by 100 in terms of percentage. So next, some of the important mathematical relations to be remembered for the pumps, for our to understand the numericals or problems, to solve the problems are listed below. Just observe one by one. So headings of the tabular columns are like this: serial number, pump factor, gear pump, vane pump and piston pump. So we have listed here few pump factors for gear, vane and successively for piston pump. So let's just have a glimpse on all of them. So first important pump factor is volumetric displacement. So what is the volume of fluid, maybe within the casing or within the cylinder if it is a reciprocating pump, within the casing if it is a rotary type of pump. Okay, VD, capital V, okay, subscript. So this should be written with a smaller font, V, capital V with a larger font, D with a smaller font. VD is nothing but for gear pump it is pi by 4 and, okay, D naught square minus DI square into W, okay, where D naught and DI are nothing but the, okay, outer and inner gear diameters. Because we have seen the external gear, okay, maybe any gear pumps, external gear, internal gear, it is a combination of gears. So the largest gear minus smaller gear, or outer gear minus inner gear. So squares of their diameters into W, where okay, capital W is nothing but width of the, okay, capital W is width of the tooth of the gear. So W is nothing but width of tooth of each gear. Okay. Similarly for vane pump, pi by 4 into DC plus DR into E into W, I repeat, pi by 4 dc plus dr into E into W. So dc is nothing but diameter of the cam ring. If you just remember the vane pumps, there is a cam ring on the outside within the casing. Next to casing is the cam ring, followed by rotor which is within. So vanes will be keeping on moving between these two, between the cam ring and the rotor, and that centrifugal force will create the suction of the fluid. So that is the core aspect in vane pumps. So addition of these two diameters is nothing but the amount of or space between the rotors is nothing but addition of these two, dc plus dr, diameter of cam ring plus diameter of rotor into eccentricity between these two, because to generate the centrifugal force we need eccentricity. We have seen in the even in the pictorial representation of vane pumps that eccentricity is required for creating the centrifugal force. Cam ring and the rotor, they are not concentric, they are eccentric. So that eccentricity will yield the centrifugal force so that the fluid gets into the vanes of the vane pump. So that is a core operating principle. So the formula holds good there, dc plus dr into E into W. W is the width of vane. So what is the width of the vane? Thickness of the vane will decide the amount of fluid which is get trapped in the volume of the displacement. So last one is piston pump. Formula is like this, AP dB Ny tan theta. I repeat, A subscript P, that is nothing but area of the piston, D subscript B, diameter of the bore, cylinder diameter. AP is the area of the piston, dB is the diameter of the cylinder bore, N is the RPM, speed of the shaft, N is the RPM, Y is number of pistons, capital Y is number of pistons, tan theta, theta is the offset angle. If you just remember the piston pumps, it involves piston, cylinder, and drive shaft. So formula is something not to be remembered, just remember the pumps. There you have something called as a piston. Piston area is directly in contact with the fluid. Then comes the area, diameter of the bore. So what is the diameter of the bore? Because between these two is the occupancy of the fluid. That is the chamber being provided. Between the area of the piston and diameter of the bore. Then you have speed of the shaft, which is one of the important parameter for suction of the fluid. Then comes how many number of pistons. So that will give you volume of pistons. Finally, the angle of the swash plate, theta, tan theta will give you, theta is nothing but offset angle or the angle of swash plate, or maybe if it is bent axis, angle of offset angle of the cylinder. Theta is nothing but offset angle of the swash plate or the cylinder. So this is about volumetric displacement. Similarly, second pump factor is theoretical flow rate. It remains same for all the pumps. QTH. Theoretical flow rate is QTH, that is discharge. Theoretical discharge is another name. VD into N. VD is obviously volumetric displacement. N is speed. The drive shaft RPM, speed. That remains same for all of them, for gear, vane and piston pumps. Last one is, third one is theoretical torque. Theoretical torque, capital T subscript TH. Capital T is of larger font, TTH. That is nothing but the product of P into VD. P is nothing but pressure developed or delivered by the pump. So what is the pressure delivered to the fluid by the pump? That is nothing but P. P into volumetric displacement. That is also same for all the pumps. And last one is theoretical power. Power is PTH, capital P subscript TH. So obvious formula is 2 pi N into theoretical torque by 60 watts. I repeat, 2 pi, because it is 360 degree. If it is rotary as well as reciprocating, 2 pi 360 degree into speed of the drive shaft N into torque being developed in the either in the rotary element of the shaft or in the reciprocating element of the shaft. T theoretical divided by 60. Divided by 60 is to convert it into usually seconds. Work done is calculated. Power is calculated by work done by time. Time we usually calculate with respect to seconds. Usually we keep the power element in seconds. Just divide by 60 is used for converting the power in seconds, watt, okay, Newton meter per second. I repeat, Newton meter per second. That is a unit of power, rate of, okay, doing work. Okay, this remains same for all the, okay, gear, vane and piston pumps, 2 pi n TTH by 60. At the last we will see one of the problem so that you get the understanding of, okay, to solve better more number of problems in piston pumps. So problem number 1 for piston pumps, okay, I'll just read out the statement. Reading out the statement itself will solve 50% of the problem. You should read, not only read it, you should listen to the problem, you should understand the problem. Okay, all these things will happen if you have a right perception of theoretical knowledge. Then if you apply it here, understanding problem is not a big problem. So if you don't understand a problem, then again solving a problem is a big problem. So just understand it carefully by reading it carefully. Find the flow rate in units of meter cube per minute. He wants us to find the flow rate. I told you flow rate is nothing but discharge. Okay, Q actual is what is being questioned here. Find Q actual in meter cube per minute. He has already given the unit also, meter cube per minute. For an axial piston pump, he has clearly mentioned it. So this is piston pump. Okay, for an axial piston pump running at 1000 RPM. I'll just read out the statement, then we'll make out. The pump has 9 number of 15 mm dia pistons arranged on a 125 mm dia piston circle. Okay. The offset angle is set at 10 degree and volumetric efficiency is 94%. Okay. So just again read it carefully for acquisition of the data. So he has asked Q actual in meter cube per minute. We have written here flow rate Q actual is question mark. That is what we have to find it. Next comes axial piston pumps. So he has given, okay, piston pump. So now we will negate all the other type of pump here, so that we will restrict our knowledge to piston pump. Is given N here, 1000 RPM. Make a note of it. N, speed N is 1000 RPM. The pump has 9 number of pistons. Okay, 9 number of 15 mm dia piston. He has given number of pistons here because the formula is here only. AP dB N into Y into tan theta. Okay, so N is, we have already noted here, 1000 RPM. Y is nothing but number of pistons here. That is what we have noted. Number of piston Y is 9. And then comes, okay, he has given the diameter of the piston is 15 mm dia. That is what we have noted here. Dia of piston is small d. 15 mm, that means to say convert into meter because we want answer in meter. Okay, 15 millimeter. Milli is 10 to the power minus 3 or divided by 1000. 10 to the power minus 3 or divided by 1000. That will give you 0.015 meter. Or you can keep it as 15 into 10 to the power minus 3 meter. Okay. So then comes arranged on a 125 mm dia piston circle. 125 mm piston dia circle is, he has given piston dia circle, that is indication of dB. Okay. He has given cylinder bore diameter 125 mm, millimeter, again I have told you, divide by 1000 or into 10 to the power minus 3. Milli is 10 to the power minus 3. So I have divided by 10 to the power minus 3, that is 1000. So 0.125 meter. Okay. The offset angle is set at 10 degree. So theta is the offset angle, that is the swash plate angle of piston pumps. So that is theta is 10 degree. He has given you, okay, set at volumetric efficiency of 94%. He has given eta volumetric 94%. Okay. Find Q actual. See, answer always, the solution is within the problem. Please do remember, we don't have anything to come out from the out of the question. So answer is hidden within the solution. So to find Q actual, whatever the data he has given, just go through them. So he has given lastly the something called as volumetric efficiency. Is there something related to Q actual in the problem? That is what we have to see. So you know that volumetric efficiency is Q actual by Q theoretical into 100. So you know volumetric efficiency. Q theoretical also is, okay, if you find out any one of them, obviously, okay, you can get the Q actual here from the formula. This is what we want now. This is already known to me, 94%. Can we find QTH with the given data? That is what you have to see. So that is what we are doing here. QTH is AP, dB, N, Y, tan theta. Okay, N, Y, tan theta. So has he given all these data? Just cross check here. He has given AP because I can calculate it with the help of, okay, diameter of piston is already given. I can calculate area of piston, pi by 4 into d square. Okay, that is what we have done here, pi by 4 into 0.015 square. dB is nothing but diameter of the bore, we have substituted. N is 1000, he has already given. Y is also 9 piston, theta 10 degree. Every data is given so that I can find out Q theoretical. So that comes around 0.0351 meter cube per minute. Since we have substituted every okay, specification in meters, we will get in meter cube per minute. Okay. So next comes volumetric efficiency formula I will utilize and calculate Q actual now. So Q actual is nothing but volumetric efficiency multiplied by Q theoretical. So we know Q theoretical, we know volumetric efficiency 94%. 94%, that is 94 by 100 or 0.94. I repeat, 94 by 100 or 0.94. We have to convert that into a number. Okay, the number they express the values or quantity. Okay, we have to understand it. So volumetric efficiency into QTH, 0.94 into theoretical discharge will give us actual discharge 0.033. 94% of Q theoretical is the Q actual. That is the meaning of it. 94% of, okay, Q theoretical, whatever you have calculated the discharge, 94% of that will be the actual discharge by the pump. This is the conclusion what we get. So if 0.0351 is a theoretical discharge, actual discharge will be 0.033, 94% of it. So this is how you arrive at a solution. Okay, if you are clear in your perception right from the understanding of pump and its performance, okay, various types of pumps, so what are the parameters affecting the pump performance, so that I will be able to give solution to the society. Okay, I can solve any reality problem with the help of proper understanding of basics or fundamentals. So this is about the complete session. So we are ending the session of, okay, pump performance and numericals. Okay, thank you. Thank you. Sir.